In this episode of the PitCon podcast, we speak to Professor Luis Colón about the power of separation science to prepare chromatographic materials.
I am Luis Colón. I am the A. Conger Goodyear Professor in the Department of Chemistry at the State University of New York. I'm also a Distinguished Professor of the State University of New York at Buffalo. And I also hold a position as an Associate Dean in the School of College of Art and Sciences. My research activities involve the study of chromatographic materials for chemical analysis. And I have a research group of about 6 students now. I say about because one is about to graduate, then it will become 5. And I just 2 months ago, I graduated my 35th PhD student from my group.
So then how did you become involved with the chromatography field?
Boy, that goes back a few years. Actually, my very first chromatographic experiment, now in retrospect, I think was in high school in biology class or something like that, I think it was, where basically we did some paper chromatography. It wasn't until I went to college that I was exposed more to HPLC or gas chromatography. But it was, what I would say superficial, it was just in the class. But when I finished my bachelor's degree, I went to the pharmaceutical industry where I actually became a practitioner of HPLC. But after a few years, I went to graduate school, and it was there where I studied chromatographic detection system for HPLC. And after that, of course, I continued doing capillary electrophoresis. And when I had my own research group, have continued the work in separation science, developing methodology for analytical chemistry, or developing materials for chromatographic separation for HPLC and for electrochromatography and for gas chromatography.
Mm. And from your experience, what have you found to be like some of the challenges of analysing complex molecules such as in pharmaceutical or environmental samples? So
challenges come and they go, and then other challenges appear, which is make our life a little more interesting. But through the years, what I have seen is that complex samples are difficult to separate. There are things like matrix effects, for example. Some of the biological samples are in these biofluids that contain literally an enormous amount of compounds that we need to separate, or we need to purify, and that becomes very challenging. So one of the major challenges, again, is to remove those matrices that are there that we don't want. There are other challenges have been identifying impurities that are such a low level that are very difficult to detect, but those we have been overcoming those, and there are other things that continue. I think nowadays one of the major challenges, I think it is that we have to have analysis in a very short period of time with a relatively less amount of funding, and they have to be quick. So I think that's one of the major challenges, although they're being addressed by many individuals in the field.
That definitely is a very perfect way to describe them. So you've mentioned a technique, HPLC. What is this technique and how would you define it?
HPLC is a separation technique, it's a chromatographic technique that basically uses a chromatographic column. This is a 2-pack with very small quantities of material and adsorbent that basically will retain compounds there, and they are retained selectively depending on the compound and the composition of the material that is in the column. And you have a solution that basically brings the sample there and then keep washing the column until the compounds are eluted out of the column and you detect them. I think that is in contrast to gas chromatography, for example, where it's similar in the sense that it's chromatography, but now it's in the gas phase, what we call the mobile phase, that take the sample to the column and then washes it out until the compounds are separated. In the gas chromatography, it's a gas. In liquid chromatography, it's a liquid. And in supercritical fluid chromatography, it's a supercritical fluid. And there are differences between the 3 of them. The gas chromatography is more amenable to compounds that are volatile. Liquid chromatography can handle compounds that are not volatile, and people have used that. Supercritical fluid chromatography, on the other hand, is a technique that uses a supercritical fluid. That's a fluid that is somewhere in between liquid chromatography and gas chromatography, and that provides some advantages because one can control some of the characteristics that really helps separate some of the compounds. And the good thing about the supercritical free chromatography is that it is a more benign for the environment, meaning that it uses, for example, CO2 that is in the environment. We collect it in cylinders, and then we use it to do the separations using CO2 at supercritical conditions. We modify it with some additive alcohols, but in general it's CO2, and then we return that to the environment again. So it's basically recycling that, and in that sense is more environmentally friendly, and more is that it gives us fast separations, and that is really helping separating things in a faster way.
Now, it's quite an interesting technique. So, kind of talking more about your other activities, could you explain what photochromism is?
So that is a process by which a particular molecule goes a transformation. Basically, most likely is an isomerization. So a molecule, a photochromic molecule, is that will absorb light, and then in that process changes its conformation, becomes something else, and now it becomes a molecule that now has a color, for example. A very good example of that are the transition lenses that we have for solar protection, I guess, for protection from the sun. So if we are inside, we have basically a transparent glass. But if you go outside, the UV light that is in the sun hits the glass, and then it changes color. So that is a photochromic compound that is there. And that color becomes now a filter in addition to that. So now the UV light doesn't penetrate and bother our eyes.
Oh, I didn't know that. That's quite cool. And why are these photochromic compounds, like, you have to forgive me, diarylethenes, or DAE, which have photoswitchable isomers, why are they so interesting, and why are they so exciting to research?
So these are very unique compounds. So what happens with these photochromic compounds is that they go transformation back and forth. It's like a switch. So shine light, convert to something, take the light out, or put a different light, and then switch back. So it goes back and forth. And most of the applications nowadays that we have are in the liquid phase, meaning that these materials are in solution. Now, the diaryl ether, what is very interesting about them is that they tend to be very stable. They can withstand more of the switching back and forth. And something that is very unique is that they do not necessarily need to be in a liquid phase, or they don't need to be in a matrix to switch colors. So they by themselves can be as a crystal, and they can change color by shining light. So just imagine now we have something, a crystal, that now we can put in, make a device, for example, that we shine light and we change something about it.
And are there any challenges associated with isolating these compounds?
Yes. The compounds, because they can go this transition, okay, they are made, and then they are, for example, in the photochemical state that they are active. But they are active, but what happens with them is that they also have what is called rotamers. So they have this compound, they have these little arms, and they are rotating all the time. And to convert from one to another, they have to be in a particular set. So that's not straightforward. So you shine light in one of these compounds, and it gives you color, but there is a portion of the compound, of set of compound, that did not change because it was in the wrong conformation. So basically you have a mixture when you do this in the liquid phase. So when you try to make a crystal, for example, and you start with that, you don't know what you have. So that's why sometimes it's not that effective when you make the crystal, because you don't have a pure material. You have a mixture of them. And on top of that, there is something that is called fatigue, that it goes switching quite a bit, and then it takes a conformation that doesn't change, it's not active anymore. So that's also a challenge. So the question is, how can we obtain each one of them? And the main idea is, if you have a compound that is locked in place, let's say the shine light, it took a particular conformation, can you use that now to make a crystal? And now you locked it there, now you can go back and forth. But the problem has been that it's difficult to separate them and to make quantities that are significant that one can do those. And that's where we have been working in the field, so that we can separate them and then collect the sample that we are interested, and then use that sample. Not quite, it could be difficult because they're isomers. So they're very, very similar in nature. So you need to have the right condition to separate them and then to go and collect the quantities that are required.
And could you discuss some of the chromatography techniques that could be used to analyze them?
So one can use liquid chromatography. We have used that, and we can separate them without much of a problem. Or we have done it anyways. What people have not done in the past is use the sophistication of HPLC with some of the, let's say, we also do a spectroscopy. Basically, we have a detection system that allows us to take the spectrum of the compounds it goes by, so that gives us a characterization. And then trying to isolate that for chromatographic purposes, what one can do is the same chromatography, but instead of being in a small column, now we use a large column, and with that large column, now we go and collect large quantities. But there is and we have, again, performed that. That was the first isolation that we did. But the main problem with that is that when you go to large quantities, now you have a lot of solvent. Now you are not as friendly to the environment, so you're using what is called acetonitrile, and you don't want to use a lot of it. In analytical quantities one can dispose easier, but when we're talking about a separation, let's say take 30 minutes, and now you're using a flow rate of 20 milliliters per minute, now we're talking about gallons or liters of this material that is produced that then is a waste. So what we have done is switch to supercritical free chromatography because, again, it doesn't use such a solvent, and that allows us to do faster separation and be more friendly to the environment in terms and not wasting so much solvent.
No, it sounds like quite an interesting technique to use for this application. So, kind of looking more to the future of this field, are there any trends in chromatography and the broader separation sciences that you are currently monitoring or looking forward to seeing?
Oh boy, there are many things. Challenges always come, as I said, and they go. The chromatography in general is very useful for chemical analysis. Things that are the challenge of separating more complex samples always is there. Because we solve one problem today, but then another one comes. For example, the separation of compounds that are in the metabolomics, for example, is a field that requires more and more powerful separation techniques. So I see a trend moving towards this using two-dimensional chromatography, where you use two chromatographic techniques that are complementary to each other, basically they are orthogonal to each other, so that allows you to do these separations. I also see the trend of doing faster separations, and I think that is something that will continue, trying to miniaturize the separation system, because traditionally at the analytical level, what is used is a column that you do chromatography running at 1 milliliter per minute, for example. I think we can do better. So if we move to capillary columns, we reduce the flow rate. If we use, for example, supercritical fluid, we remove also solvent. I think there is more emphasis now in trying to create more sustainable ways to do chromatography. And I think we know how to do it, but I don't think that people really had the motivation to do it. And I think we have become more conscientious about the environment. And I think that's a trend that I can foresee continuing. And another one is the a trend towards having personalized medicine. And that separation sciences really play a big role there. I mean, we would like to have something you stick it in and get the color and tell you something, but it's not quite as simple as that. So I think now using, for example, microchips and use separation in a very small device. So I can envision in the future having go to the physician's office and they have one of these devices, and you perhaps put a drop of blood and then things get separated, and then there's a system that can detect what they are there, and so on and so forth. So those are areas that I think they're going to continue, and I think again separation science will play a role there.
No, definitely. I think personalised medicine is such a big topic, and it's almost like people forget that separation science is the foundation to how the technology is going to work. So first of all, congratulations on being the recipient of the Down the Go Award. How does it feel to win this award?
Oh, thank you very much. You know, it gives me a sense of satisfaction because the work that my students have done and my collaborators that we have done in my laboratory is being recognized, and I think that's a sense of accomplishment. I think it's also a sense that the work is important. So it's recognized because people have recognized that there is value in it. And it is interesting, I was talking to colleagues recently here at the meeting, that we do some things, it's exciting, and we move forward, and then we go to another project, and it is not until 5-10 years later that you realize that has been picked up somehow. And people are using some of the technology, may have improved, but the principle is the same. And I think it's a sense of satisfaction for me and for my students, because they feel that they have contributed somehow to the field.
And building more on kind of this topic about face-to-face meetings, and we spoke a little bit about the impact of the COVID-19 pandemic has had on events like PitCon. Why is it so important for these events to continue to take place, and for academics and industry professionals to actually encourage each other to attend these events?
I think the reason for that is that human touch, human contact, you can't replace that. And it's not the same when you are in front of a screen. So having these meetings in person is completely different. People may argue, well, but the science is the same, you can really communicate that. Yes, but it is not so dry and so cold. I mean, there is a human aspect to it. And I think you can only find that when you meet in person. There's no way around that. Something that Pittsburgh Conference and other conferences have instrumentation, and they have certain lectures, plenary lectures that are very unique. But I know it's expensive for companies to come and do exhibitions to meetings like this. However, I think it has something, again, being here and see the new instrument and touch it, and that gives a sense of that is different, and ask questions to the person that is trying to promote the particular instrument. So I think there is a lot of value into that, and I hope that continues.